topological insulator to get a magnetic topological insulator. Those materials will suffer from disorder. So I'll keep the story short. One of this material is manganese bismuth telluride. Whether there's 6 layers or 5 layers, they happen to be very different type of insulators. This really interesting layer thickness dependent phenomena. And if you have even layers, they're antiferromagnetic. If you have odd layers, they're ferromagnetic. So, and this is basically a magnetic structure, how you can manipulate them through different phases. So I'm going to tell you about magnons, of course, right? So this is my topic today. And in fact, it's not always clear how you establish a long-range magnetic orders maintained in these magnetic materials. So magnetic fluctuation would actually get enhanced when you make the layer thinner and thinner. Oftentimes, they become unstable. The magnetic order become unstable in a monolayer limit. So this is, I would argue, detecting magnons is the most reliable way to establish there's a long-range magnetic order. People do MOC measurement or they do MCD measurement, but MCD measurement is only a testimony for their spin polarization. It doesn't mean there's a long-range magnetic order. So this is a challenging thing to establish in these materials. Okay, so I won't, bore you with the detail, but just to say, these magnons in this material are detected with Raman. Somewhat special, very low frequency Raman. With BLS and Raman, we can actually have a gap-free detection. So this is, I'm switching units on you now. I've been using gigahertz, right? So now I'm using inverse centimeter. That's what everybody uses in Raman spectroscopy. And 1 inverse centimeter is about 30 gigahertz. Okay, so using Raman, the best you can do is about 4 inverse centimeter. That's 120 gigahertz. And so 120, my BLS spectrometer can measure up to 300 gigahertz. So I have a gap-free way to measure this collection. There's only certain modes that are active in Raman spectrons. And we couldn't measure magnon in a single layer of this material, but we can measure magnon in 2 layers. And that's important because 2 layer is the thinnest material where it still have a non-trivial topological electronic band. So we are able to measure, how these, this is the magnon mode, this is the phonon mode. And we're able to measure how the magnon mode, the intensity of that changes with the neo temperature. This is where exactly it's useless right now because it has an 18K neo temperature. So I should say, people has been making very steady progress of pushing the magnetic transition temperature to room temperature in van der Waals material. And there are compounds that exhibit that now. So again, I won't pretend I know what's gonna be useful. Just to say there's a lot of people very invested in studying these materials. By looking at the magnon mode, how they evolve with external magnetic field, we can map out the magnetic phases, AFM phases, canted AFM phases, and ferromagnetic phases. And also importantly, we can use the spin wave dispersion to extract some important parameters. This is a single ion anisotropy. This is some exchange parameters. We can also measure the magnetic fluctuations and show that the magnetic fluctuations are enhanced in the thinner layer. This should not surprise anybody. But also these magnetic fluctuations exhibit singularity near the neo temperature. All of these are somewhat expected, except for it's not easy to measure them in these ultra-thin samples. You can use this method to compare different kind of van der Waals magnetic materials. Different magnetic materials have different properties. But let me just go to the take-home message. So using magnon spectrons, you can identify phases in very thin van der Waals materials. And you have selection rule that determines by both the crystalline symmetry and the magnetic order. By measuring the spin wave gap and anisotropy, you can extract important parameters on these ultra-thin films. And there are some very narrow two-magnon resonance that could be related to topology. So, and with that,